Hi and greetings. Welcome to my keynote presentation entitled Thermodynamic Analysis of Fuel Oil Blended Stocks or FOBS to Liquid Hydrocarbon. This study was conducted by Teo Mi Lian and supervised by me, Zaki Yamani Zakaria, and also Mazura Juso. We are from the School of Chemical and Energy Engineering, University Technology, Malaysia. The following is the flow of our presentation today. First, I will be covering the introduction, followed by literature review, and then it will be continued with the methodology, result and discussion, and finally conclusion. This is the first part, the introduction part. In the introduction, I'll be covering the research background, problem statement, objectives, and also scope. Over the past century, we have been highly dependent on fossil fuel as our main energy consumption. Even though fossil fuels such as petroleum, natural gas, coal is diminishing, we are still depending on it. International Energy Outlook 2016 mentioned that fossil fuel will still be prominent compared to renewable energy in 2040. Even though technology and the advancement have shown that renewable energy sources can be used, well, it is still pretty much underutilized and the consumption and the application is still quite limited due to price constraint. Because of the depleting fossil fuel, we must look for alternatives. There are plenty of alternatives around us that maybe we have not even realized, but there is one alternative feedstock which is called fuel oil blended stocks, or known as FOBS. What is FOBS? FOBS is actually an undesired product in the petrochemical refinery. It is a product that creates environmental and also financial as well as storage and treatment concern as well as problem. Therefore, we need to know how to actually deal with FOBS. FOBS is actually an undesired product that existed in the petrochemical refinery, and it is very difficult to be processed. Hence, there are plenty of limitations of FOBS, but it has tremendous potential. So we need to know how to tackle FOBS. We also need to think on how we can convert FOBS, which is actually having higher hydrocarbon number. Then we need to break it down to a more reasonable hydrocarbon range that can be used for gasoline, kerosene, and so on. We also need to think of how to upgrade FOBS, as such that I mentioned just now, to upgrade it to better and more application hydrocarbon. Hence, this can be proven as a solution for the oil and gas or energy issue, the energy limitation, fossil fuel depleting. So this can be a solution for it. So we need to see how we can actually utilize the best out of FOBS, and this can be a solution for the plenty of issues regarding the environmental regulation law and so on that actually portray that FOBS is actually a problematic issue. FOBS actually consisting of 20 plus or 30 plus complex carbon, complex hydrocarbon. So it's our desire to break down the FOBS into smaller range of hydrocarbons such as C5 to C10 as mentioned just now. So there are several methods to break it down using a cracking process. So there are three methods of cracking, conventional methods, which are thermal cracking, catalytic cracking, and hydrocracking. We realize that it is not easy and cheap to conduct plenty of cracking experiments. Hence, we come out with another alternative, which is a thermodynamic modeling study. We know that, okay, here comes the problem statement. We know that FOBS is a constraint in the refinery. As such, it creates environmental concern, financial problems, and so on in order to treat it or to dispose it. Hence, it is a definite problem in the refinery. At the same time, we would like to convert okay, because this is a concern for the refinery and they don't want it. So we want to find an alternative solution, how to make full use or better use of the FOBS. So that's why we want to actually crack it down to lower hydrocarbon rich by using cracking. And we are going to do a thermodynamic modeling to crack down, to investigate, to see whether the possibility is there. There are no similar or particular research about this yet, about the breaking down, the thermodynamic modeling of breaking down a model compound of FOBS that we have discovered yet so far. So we are planning to actually use n-Eicosane as a model compound to represent FOBS, to break it down, to study whether it is possible or not. It is, of course, FOBS is quite a complicated hydrocarbon and is a mixture of many things. But in order to make full use and better study of this research, we decided to use n-Eicosane as a representative. Hence, the objective of the study is actually to determine the reaction that may take place during the conversion of FOBS into liquid hydrocarbon. Second, to investigate the major products of cracking FOBS into smaller liquid hydrocarbon. To investigate the effect of reaction parameters of different temperature and Eicosane to oxygen molar ratios on the composition of product in equilibrium. So those are three objectives, and the scope of study is we are going to do a simulation, a thermodynamic simulation, and we are going to employ total Gibbs energy minimization method to identify possible reactions. Now, let's move on to the second part, the literature review. There are plenty types of FOBS, and the FOBS that we are considering in this study is from the heavy fuel oil, or what we know as HFO. HFO is one kind of FOBS besides other category of FOBS available in the refinery. And from HFO, we are going to use n-Eicosane, which has carbon number of 20 to be used for this study. For your information, HFO contains saturates, aromatics, resins, and asphaltenes. So it's basically a mixture of many compounds, and it's very difficult to be used as a normal fuel. It has high specific gravity and viscosity, and upon burning or processing it, it can actually release toxic particles. It is normally appearing as a dense material due to the existence of asphaltene. So in this study, we are going to decide to use n-Eicosane as a representative, as a module compound, because n-Eicosane has been found to be available in abundance in HFO, besides the other materials such as the saturates, aromatics, resin, asphaltenes, and so on. And for the sake of this study, it's better to use n-Eicosane because it is simpler. Hence, after knowing the result, then we can add on more complex material bit by bit. The table shown here shows the technologies for the upgrading of FOBS that were obtained from the references from the literature. So we have here several conventional methods of cracking, which consisted of thermal cracking, catalytic cracking, hydrocracking, and also cracking with oxygen. And in this study, we are going to perform a thermodynamic modeling of the cracking of n-Eicosane with oxygen. We are going to perform cracking of FOBS together with oxygen. And why do we do cracking with oxygen? Well, basically, we would like to reduce the release of harmful impurities or toxic material from FOBS. We also want to increase the production of light fractions and also reduce the formation of coke. And we want to reduce the CO2 emission or release to the atmosphere. And because of that, we are adding on oxygen, but we are going to control and we are going to limit the oxygen to below 8% for safety purposes. In any thermodynamic modeling studies, besides deciding on the raw material or feed material, we also need to decide on the products. In this study, we have decided on several products that include alkane, alkene. The alkane include methane, ethane, propane, and so on until C10. And also for alkene, we have considered the likes of ethylene, propylene, butylene, and so on as well. Besides that, the main energy that we are going to try to get from this study is actually hydrogen. And besides hydrogen, that we consider as the alternative energy or renewable energy sources that we want to obtain, we also anticipate the production of CO, CO2, water, carbon, and so on. So there are plenty of products that we have considered in this study. There is a reason why we want to perform thermodynamic analysis. This is mainly because it provides a clear vision of the feasibility of the process and also reduce testing costs in the real situation. And there are plenty of softwares that can be used, can be employed for performing thermodynamic analysis, such as HSC Chemistry, Aspen Plus, ChemKin Code, and others. Now let's dive into the methodology section. I'll be describing the detail of our thermodynamic modeling study. We actually employed HSC Chemistry version 11.0 software, and we used the total Gibbs free energy minimization technique to actually perform the thermodynamic modeling study. We decided to employ n-Eicosane, which is C20H42. That's the chemical formula of n-Eicosane as the model compound, and also the oxygen as the co-reactant. And the reaction parameters is temperature, and we control the temperature between 573 Kelvin to 1273 Kelvin. The pressure is controlled at 1 bar. The ratios of n-Eicosane to oxygen is 0.5 to 0.5, 0.7 to 0.3, 0.8 to 0.2, 0.9 to 0.1, and also 0.95 to 0.05. I'm sorry that you cannot see it there. We have made several assumptions for this study. First, the total reactant input was set at 1 kilomole in every condition. The outer composition of the product was assumed to be in equilibrium at the exit of the reactor. The formation of minor byproduct was not considered in this study, and the mixture of ideal gases was consumed. Carbon is the only solid. We employ HSC Chemistry version 11 software for this thermodynamic study. We just need to seek for the raw materials, decide on the reactions, decide on the products, and this can be done by studying the literatures extensively. We decide on the mole, we decide on the temperature and also pressure. We understand that the principle of the software of the study is based on total Gibbs free energy minimization method, and by having the background calculation and so on, the result will be generated and we analyze the output with great detail. The result and discussion part. In this study, we have decided on 20 reactions that will be involved in the cracking of n-Eicosane with oxygen reaction. The type of reactions range from the cracking of n-Eicosane, partial oxidation of n-Eicosane, dehydration of ethane, methanation, reduction of CO, and much more. The figure shows the proposed reaction network based on the main products formed in the cracking of n-Eicosane with oxygen at 1 bar. The cracking process begins with the main reaction that requires high energy to crack n-Eicosane into smaller hydrocarbons. Then, a free radical mechanism that involves the C-C bond homolytic scission occurs. Each of the first products undergoes secondary reactions respectively until an equilibrium condition is achieved. The cracking of smaller components and side reactions occur as well subsequently. No aromatic or branch olefins were recorded in the product equilibrium composition. Only linear alpha olefin was found in the outlet composition. The reaction products include hydrogen, coke, methane, water, carbon monoxide, carbon dioxide, ethane, ethylene, and acetylene, while the minor products include C3H4, C3H8, which is the propane, C3H6, which is propylene, C4H6, butane, and also butylene. Among the main products were hydrogen, carbon, and methane. Those chemicals recorded the highest value of the production among the others. It was found that the percentage of oxygen conversion is 100% in all n-Eicosane to oxygen cracking reactions. Figure 2a shows the yield of hydrogen produced, which is increased with the increase in the temperature. The highest number of moles of hydrogen produced can be seen in the highest n-Eicosane to oxygen ratio. The rapid increase in the production of hydrogen in the early stage is mainly contributed by the cracking and also partial oxidation of n-Eicosane with oxygen. The high yield of hydrogen in this process is beneficial, as hydrogen has a variety of uses, and this is our main fuel that we want to produce and to obtain. Figure 2b shows the amount of carbon being produced with temperature at 1 bar at various EO ratio. We can see that the highest coke or carbon being formed at n-Eicosane to oxygen ratio 0.95 to 0.05. Even though we are not employing catalysts in this thermodynamic study, yet carbon is still being formed. Figure 2c illustrates the amount of methane being produced from the cracking of n-Eicosane with oxygen at 1 bar. We can observe that the amount of methane is being produced more at lower temperature, while it slowly, gradually decreases when it reaches higher temperature. Similar to carbon formation that we discussed earlier, more methane is being produced in the higher n-Eicosane to oxygen ratio due to the presence of more carbon in the reactant. In these figures, we can see the comparison of two products, carbon and methane, and which products dominates more at the lower temperature side versus the higher temperature side. And we can see that methane prevails better compared to carbon at the lower temperature side. The figure here shows the production of water at the cracking of n-Eicosane with oxygen at 1 bar. As we can see here, as the temperature increases, the water production drops. And we can see that the low n-Eicosane to oxygen ratio, which is 0.5 to 0.5, promote the highest water production, but still when the temperature increases, it goes down. Even though water is not what we desire, it is still a better environmental product compared to others, such as the FOBS itself. The reaction involved here is mainly the methanation of CO and also CO2. At the lowest EO ratio, or n-Eicosane to oxygen ratio, the presence of more oxygen promotes the highest production of both gases. When the temperature of reaction increases, the moles of CO produced increase. On the other hand, the amount of CO2 produced at low EO ratio increases slowly until it achieves the maximum range of around 800 to 900 Kelvin. From here, we can conclude that oxygen induces the cracking of n-Eicosane by enhancing the selectivity of COX in products formed compared to the traditional cracking. The addition of oxygen in cracking is a more environmentally friendly process than the traditional cracking process. Let's look at the ethane and ethylene trend. The main cracking reaction mainly triggers the production of both products. The higher EO ratio promotes higher production of both gases due to the availability of carbon in the reactants, which is in the FOBS. Number of moles of ethane increase to a maximum point of around 750 Kelvin, while ethylene conversion increases with the increase in temperature in all EO ratios. From previous slide, we can say that ethylene is being produced from ethane through the dehydrogenation of ethane. Where the temperature increase, the production of one olefin is higher than the normal paraffins with more than one carbon. And for conclusion, the most important information that we obtain from the cracking of FOBS with oxygen is that hydrogen and methane, which are precious energy source, can be formed from FOBS. And besides that, carbon is also being formed in abundance as well. Methane production is optimum at EO ratio of 0.95 to 0.05 at 573 Kelvin at 1 bar, while hydrogen production is optimum at EO ratio of 0.95 and 0.05 at 1273 Kelvin at 1 bar. We know that atmospheric pressure operating condition is cost-saving compared to a high-pressure condition, which needs extra safety concern, and that's why we employ and use the atmospheric pressure condition. The uses of oxygen to induce the cracking process is very convenient. Only minor modification is required to supply oxygen stream into the reactor. And last but not least, we can say that the simulation is successful. We can learn, we can know, we can discover everything in the shortest possible amount of time. Thank you very much for staying here until the end of the presentation. We appreciate your time and we welcome any questions. Thank you very much.